Our next video is going to be a slightly more relaxed example. So we'll introduce the example. I do want you to solve this one on your own. It should be a little bit more manageable than our last one, which was really quite gnarly. But yeah, so in this situation, what we're going to model is, whether my cat will get off of my notes, I do need those. What we're going to model is, what if we have a flat table? So no more book propping up our table. What if we have a flat table and we have some oscillation, but then all of a sudden, at some moment, an earthquake starts? So the way that we're going to model that is with the differential equation with a sinusoidal discontinuous forcing function. So here we go. Example. Solve y double dot plus 4y. Oh, that's it. It is not damped. Is equal to 3 times u sub 5 of t, our Heaviside function that turns on at 5 seconds, times sine of t minus 5. So the right-hand side is saying, okay, for the first 5 seconds, right, nothing's happening, and then we have an earthquake that's giving us oscillating forcing, okay? And what we're going to do is we're going to solve this with the exact methods that we've been showing this whole section, where we start with qualitative analysis, and then we solve it with the Laplace transform, and we make sure that it all checks out. So what does our qualitative analysis look like? Qualitative analysis, we know this is undamped. We know the natural period. All right, because our eigenvalues of the undamped, or the unforced one, are going to be plus or minus 2i. So the natural period will be 2 pi over 2, which is pi. I wrote period twice, didn't I? And then the period of the forcing function is 2 pi. So we don't have resonance. Our solutions are going to stay bounded. Remember, if that forcing function goes with the natural frequency, if they're in phase with each other, then it will grow without bound, and this mass is going to go flying off the table eventually. Maybe a small exaggeration. Okay, and furthermore, since it's undamped, right, we have harmonic motion. It's going to be a center. Our equilibrium is going to be a center. We know its period. We know it's going to be oscillating, and then, yeah, we'll be adding a forcing function, but it'll still just be oscillating, and even over here, it'll still be bounded oscillation. So what we might expect, oh, can I give you an initial condition maybe? I didn't actually give you an initial condition. That's interesting. Well, we're going to need one. Let's say the initial condition is my favorite initial condition. Well, this is actually really quite boring if the initial condition's too boring. Let me find an initial condition here. Let's start not at rest. Well, y of 0 will be 1. Y prime of 0 will be 0. All right. So we're starting out stretched to a position of 1. It's undamped, so we'll oscillate until the earthquakes start, and then things will shake up a little bit. No pun intended. So we're guessing this is what our function might look like. We're starting at 1. Our period is period's pi before the forcing starts, so it's about 3. So it might look like something like this. And then forcing happens, and it'll be some kind of new oscillation. I don't know what the new oscillation is going to be. Maybe it's smaller, or maybe it's bigger. I don't quite know. We could calculate it. But there's going to be some change. And again, we do have undamped before and then undamped after. And maybe it'll be like, maybe it'll have like one of them will be high, like it'll alternate. Who knows? But this is what we are kind of going to expect, qualitatively speaking. Now we're going to solve it with the Laplace transform. And here is where I want you to pause the video. It won't be as bad as the last one, I promise. Well, and then see what we get. So if we use the Laplace transform, we can take the Laplace transform on both sides. We'll get the Laplace transform of y dot, which is just going to be s L of y dot. Sorry, y double dot is what I meant. Minus the initial value of y dot plus 4 times the Laplace transform of y equals 3 times the Laplace transform of all this stuff, which we do have a property for, which is nice. This becomes s squared L of y minus s y of 0. The original derivative, right, our initial velocity was 0, so that part goes away, which is nice. Just left the 4 L of y. And how do we take the Laplace transform of some kind of shift with a Heaviside function? Well, we consult our table. Our properties. Okay, it's just going to be e to the negative 5s times whatever the other Laplace transform is. So this will be 3 e to the negative 5s times whatever the Laplace transform of sine of t is. And so it's t minus a, but there's no t minus a over here. It's just going to be f of s. So for sine of t, what is f of s? That's omega is equal to 1. Sine of t is going to be 1 over s squared plus 1. So we know that this is just going to be f of s over here. So we can divide it by s squared plus 1 like so. Now we just combine the L of s's, or sorry, the L of y's together. We're left with s squared plus 4. And y of 0 was 1, so this just becomes a minus s. We can add s to both sides. So we'll get s plus 3 e to the negative 5s over s squared plus 1, like so. Divide both sides, and we'll get L of y by itself. S over s squared plus 4, that's not too bad. Plus 3 e to the negative 5s over s squared plus 1, s squared plus 4. Okay, that's going to be more exciting. We'll use partial fractions on the second one. We'll need to take the inverse Laplace transform of both sides. And again, hopefully you have already worked on this and you're checking your work. If not, pause the video, try to take the inverse Laplace transform right now. And what you're going to get is y of t, the inverse Laplace transform of s over s squared plus 4. What does that look like? S over s squared plus 4. Ah, okay. It looks like this. Sine of omega t, where omega is 2. So, oh wait, sorry, s. I did that earlier too, right? S over s squared plus 4 is exactly sine of omega t, for omega is 2. So this will be, sorry, cosine, gosh. Cosine of 2t over here. And what is this other part? Well, that's more complicated. We're going to have the inverse Laplace transform of 3 over s squared plus 1, s squared plus 4, all times e to the negative 5s. So we know it's going to be some kind of shift on the s-axis. Right? We know we're going to be able to use this property over here. We just have to find out what is the inverse Laplace transform of that other part. And we'll use partial fractions for that. So let's go off to the side and find this. And actually, I'm going to give myself more room than I did last time. We are going to go off to the side on the next page. That'll be as plus b over s squared plus 1 plus cs plus d s squared plus 4 multiplied by the LCD. We'll get as plus b s squared plus 4 plus cs plus d s squared plus 1. And when you put, this needs to be true for all s, so specifically when s is 2i, it should be true. That'll give us that 3 equals 0 plus 2i is going to be 4i squared, negative 4, this will be negative 3. I feel like we've already done this exact same partial fractions. Negative 1 is CS plus d. Oh, sorry, s was 2i. So this is c times 2i. I was getting a little concerned there. In other words, c is 0 and d is negative 1. You do the same process with s is equal to I, and you're going to get 3 is equal to I squared is negative 1. We get 3 times ai plus b plus 0. And again, you're going to get a is equal to 0 and b is equal to 1. So this whole thing will be just 1 over s squared plus 1 minus 1 over s squared plus 4. And those will both be signs, I believe. Yep. Signs. This one will take a little bit of work, but not that much. So let's take that to the previous page. I think I don't actually go backwards that often. We should get this. Put it over here. So we're looking for the inverse Laplace transform of this times e to the negative 5s. So it'll just be this and then kind of shift it over. So here is going to be omega equals, is it negative 1 or positive 1? Positive 1. And here is going to be omega equals 2. And again, this is for sine of omega t. This is also for sine of omega t. But here, in order for omega to be 2, we have to multiply by 2 and divide by 2. And then we'll use the property down here. Okay. It'll just be the Heaviside function at 5. And then the original function shifted over 5. So we'll get cosine of 2t plus, this is going to be sine, well, Heaviside function, right, at 5 of t times sine of omega t, but shifted over. And omega is just 1. So it'll just be t minus 5, like so. And then this becomes minus 1/2, the same thing, basically. But now omega's 2. So it'd be sine of 2, t minus 5, like so. So not as bad, right? Not as bad as the solution before. Let's see if this models and reflects the qualitative behavior that we said. It should be oscillating with no damping, and then at 5 seconds, something changes. Depending on where we are in the cycle, which we didn't quite calculate, it'll either make our oscillation smaller or bigger. And again, we'll just still have oscillations. Let's plot the function. I think I have this somewhere. Starting with a cosine of 2t. Not this one. Is it this one? No. All right, we haven't graphed it. Well, we can graph it. All right, so a is 5 here. Then what we're going to graph is our function, which is cosine of 2t, plus ua of t times sine of t minus 5 minus 1/2 sine of 2 t minus 5. Let me just double check that I wrote it down right. Great. If we zoom out, we can see the behavior. Yep, for the first 5 seconds, it's just oscillating normally. And then we can see that sinusoidal forcing function. And again, it does have those one bigger, one smaller, like we were kind of postulating could happen, and that we saw very similarly with an earlier example. So once the earthquake starts, we don't have resonance, but we do have, and we don't really have beats because they're not close in frequency, but we do have this sort of like double oscillation moment, or like kind of two different amplitudes that they're switching between to kind of show it. There we go. That's great. And we could look really quickly if we wanted to about like, okay, what is, let's call this G. What does its derivative look like around 5? And you see the derivative is also continuous and seems to be differentiable at 5. Right. Let's zoom in on 5, really see what's happening here. Sorry, 4.5 to 5.5. All right, at 5, the derivative also seems to be continuous. What about the second derivative? Oh, it's bigger. We need to zoom out. Oh, interesting. So the function, let me show you what we have. The function in blue is continuous and differentiable. The derivative in pink is continuous and differentiable, but the second derivative at 5 is not differentiable, but it is continuous. So the fourth derivative, if we wanted, or sorry, the third derivative rather, is discontinuous. So yeah, there's a discontinuity somewhere. You just have to take a couple derivatives to get there. All right. That's it for this video. We have one more video in this section on what does resonant forcing look like here with the Laplace transform, and it'll be pretty cool. And actually we have one of our first pieces of good news. It'll be easier. Tune in next time, which is hopefully very soon, to hear more about that.